session is called titled Collaboration, and we have very interesting 3 papers about collaboration in VR and AR. The first paper is from IBM Research Group, titled Immersive Insights, Hybrid Analytic Systems for Collaborative Exploratory Data Analysis. And the authors are Marco Cavallo, Michel Dolaika, Matheus Havlena, Ken Ochtree, and Mark Podlesek. And we have today Marco as a presenter here. So Mr. Marco Cavallo graduated in computer science and engineering from Politecnico di Milano in Italy, and also University in Illinois, Chicago, which is renowned for cave systems in electronic visualization laboratory. He has been working at IBM Research in New York, where he worked on applications for AR and VR technologies for visual analytics in the context of data science and healthcare research. Recently, he joined Apple in California. He's currently working on data visualization for machine learning and computer vision algorithms. So let's welcome Marco. Thank you.
Okay. Thanks a lot for the introduction. So as Ken mentioned, today I'm going to be presenting a work that I did in collaboration with my former colleagues at IBM Research. The title is Immersive Insights, a Hybrid Analytic System for Collaboratory Exploratory Data Analysis. Let's go quickly to the definition of exploratory data analysis, which is, we could call it the process of performing initial inquiries on a data set, and the goal in this case is to discover interesting patterns, spotting anomalies, testing hypotheses, and checking assumptions. In short, we have a data set and we want to make sense of it. We would like to understand, for instance, which structures are in the data set. We want to try to validate some hypotheses that we have about distributional information. We want to try to understand how many dimensions map to each other, how they correlate, and eventually identify which are relevant to our task. We have many, I would say, data visualization tools for exploratory data analysis. You can see some recent examples here. And in this case, you can see that they're mostly web-based and single user. Generally, it is hard to build something for exploratory data analysis in general, because it is a very broad field. There are too many algorithms, there are too many ways, there are too many paths to arrive to the same solution. And in this sense, it is hard to build deep enough general purpose tools, also because you generally need some domain expertise. You generally have something that's very specific to the task at hand that you need to do. And another problem is generally reproducibility. That is what I call getting lost in ADA. Generally, data scientists or data analysts try many different ways to arrive to a solution, and it's generally difficult to trace back how they arrived to that solution. Another difficulty is collaboration, because as I mentioned, most of these tools are actually single user. A quick note here, when I write very broad field, it also means that it encompasses many types of data. For today, we are mostly going to focus on tabular data, so like structured data. However, this is an AR/VR conference. So the question here is, how can we use AR/VR to improve exploratory data analysis? And here I'm going to give a very brief background in immersive data visualization or visual or immersive analytics. You see 2 timelines, one for head-mounted displays, one for immersive environments. Here the idea is that with AR/VR, we generally try to see if depth clues, perspective, larger amount of space, because normally it is kind of cumbersome to handle certain data and fit it on a 2D screen. We can see if these things can be helpful for exploratory data analysis. This presentation was originally in Keynote, so we are going to see some unexpected animations eventually, so prepare for it. So we start in the 1965 with Ivan Sutherland, and we have the first prototypes, and in this case you can see how headsets are limited by the hardware at the time, and you can see these bulky prototypes. On the other hand, in the 90s we had the introduction of cave systems. Pretty much, probably all of you know what a cave system is, but I would say it's a cube on which like 5 faces have projections, and generally this is used with stereoscopical 3D to visualize 3D or spatial data. In the early 2000s, with the drop in the cost of LCD panels, we observed what we can call power walls or large display walls. And in this case, we have much higher resolution, but generally with the decision of sacrificing 3D rendering. Later on, with the introduction of what sometimes are called hybrid reality environments, you can have both 2D and 3D information at the same time. For us to have like some developer kits for headsets, we had to wait until 2013 and 2016 for the HoloLens. And at that point, the question is, what's going to happen between these two timelines, headsets versus immersive environments? At least for my personal work, what we introduced was data space in 2018, which we presented at IEEE VR this year, where we try to combine immersive environments with augmented and virtual reality headsets, so as to have 2D information for high resolution statistical information, and AR/VR for 3D rendering. Then the question here could be, what's going to happen next? Definitely, we are seeing a boom in headsets. We know a bit less of what's going to happen to immersive environments, but that's a different story. So now that we have all these fancy AR, VR gadgets, so how can we actually use them to improve exploratory data analysis? And as we said, we can have different types of contributions. Normally, when you do exploratory data analysis, you want to see many things at the same time. You want to have context, you want to have detail, you generally have many different tabs, and it's generally hard to keep them all at the same time during the analysis. So a possible contribution is having a larger working space. At the same time, arguably, we can have a better interpretation of higher dimensional data, collaboration, and personalized analysis. So for instance, everyone could have its own slice of data and eventually see it from a different perspective. However, we have a big challenge. So pretty much this challenge is the current hype in VR, AR technology. So you can often hear advertisements about, oh, we are going to show you this amazing 3D scatter plot in your HTC Vive, and you're going to magically make sense of your company data. Or we can see very, simple or naive research papers where you can see 20 data samples, you see 10 participants, and then they say, oh, this is much better in AR, VR than in real life. The truth is that exploratory data analysis is very complex, and it's hard to boil it down to these simple things. So that's why throughout this presentation I'll try to pinpoint how deep we need to go and be rigorous in terms of analyzing the advantages of AR and VR. So again, while sorry, I have little voice today. So while it has been demonstrated in various cases advantages of VR for certain tasks, it is still a bit unclear how AR/VR would perform in the context of ADA at large. So what we try to answer today is, which level of immersion would EDA benefit from? Would it be good to have a HoloLens? Would it be good to have a cave? Should I have an HTC Vive? And can we quantify how much AR and VR are actually useful? And finally, how can we design a fully fledged analytics system that seamlessly integrates AR and VR? So this is why we present our system called Immersive Insights, and we are going to propose a user study to discuss a bit more about these questions. I'm going to do a very quick introduction about data space. That is the system that we built Immersive Insights on. We call it a configurable hybrid reality environment. Hybrid reality because we have 15 high resolution displays to show statistical information, where you generally have dense text or charts that actually require high resolution. On the other hand, we have 3D content through HoloLens and Magic Leap devices. And then we have a table at the center where you generally have aggregate information, and that's mostly to foster collaboration. We call this concept like flexible data immersion, because in data space you can go from having a full virtual reality experience with a VR headset to having just a table and a physical environment. So you can sort of move across the virtuality spectrum. again, mini background on how this thing works, because it's a slightly of a complicated system. To make it short, it has a 3D model of the environment itself. So it's pretty much like a 3D model with the tables, the screens, and the lights, and where they are in space. We have 8 Kinect V2 sensors that create a point cloud, and then we detect where people and objects are in the environment. And then we overlay this with the mesh created at runtime by the HoloLens. And pretty much, this allows us to know where a person is with respect to other people, with respect to a screen. So for instance, I could say, okay, do this action, and this action is going to happen in the screen next to me because the system knows that I'm next to the screen. Similarly, if a person is speaking, we can rotate all the content or move the physical screens next to this person and so on. I'm not going to talk much about them in this presentation, but as you can notice, the screens are actually connected to robotic arms. So you can actually move screens physically next to people. So this is an example image in which we have a virtual representation of the environment. And on the top, you can see how an AR user would see a remote participant, and at the bottom, how the remote participant would see the experience remotely. So let's see if we can show something a little bit about the video. So very quickly, so Immersive Insights, again, is an application built on top of data space. It's actually a web application. So it's mostly done with React.js, WebGL, and the usual Python, scikit-learn and co as a backend. As you can see, we have statistical information on the screens that we call data views. Then we have a central AR area where we generally have one or multiple scatter plots of high-dimensional data. And then we have the table. Let's start with the data views. Since I don't want to make it like a system manual, so I'm gonna go very quickly over these things. But few design notes are, for instance, the concept of data instance. Normally, on a 2D screen, there is not enough space to handle too many subsets of the data at the same time. The concept of data instance, for us, it is you have a subset of the original data samples and data dimensions. You apply your clustering, projection algorithms, and metrics to this instance, and this is what defines an instance. So it's pretty much a slice of data that you're operating independently. And through colors, you can operate on multiple of them at the same time, enabling parallel analysis from multiple data scientists. Sample data views that can be loaded through voice or other gestures. The table view, the projection, clustering, distribution, correlations, feature selection, feature filtering, and feature engineering. The table view, a bit more interesting, is the way we try to make people work together. So generally, it's where you can see all the solutions and data instances you're working on at the same time, and you can discuss about the algorithms that you're using on them. You can say, oh, I found this insight in this subset of the data. Oh, does it hold for the other part of the data? Let's put them together and see if this hypothesis holds. This is fundamental also for keeping track of the data instances. So on the table, for instance, you can see, I want to know data table is green, so it's associated to the second solution. I'm going to check the data table on the table, look up, and the screen for the data table is going to be in front of me. So it's useful for finding where my data instances are, and at the same time for comparing solutions. Let's go quickly to the AR integration. So, as I said, we use AR to visualize scatter plots of dimensionally reduced data at the center of the room. As I mentioned earlier, a 3D scatter plot by itself doesn't do anything, and we wanted to enhance this concept, and we added what we call projection axis. Our implementation is ProLines that we presented in another paper. And the idea here is that once you have multidimensional data, you generally lose the connection to the original data dimensions. So you need to find ways to understand how these data features are projected into space and how they make points stay where they are. Another, I would say, AR, VR convenient application that we had is the backward projection. The idea is that I can air tap or select a data point, drag it into space, and see how its feature values will have to be modified in order to accommodate for this change. To give an example, I have Italy, I have a data point corresponding to Italy, and I wanted to go closer to the cluster containing the United States. I would physically drag this point, and then the system would tell me, okay, Italy should probably increase spending in research by X millions. You should probably decrease spending in other things by this much. And this way I can generate, formulate, and validate hypotheses. At the same time, the interesting thing is that scatter plots of dimensionally reduced data are very quick for understanding the structure of the data, but they don't provide much information. And the good thing here is that we can see with our HoloLens the dimensionality reduction, and in parallel see the higher resolution statistical information on the screen. And the fact that the AR projection is at the center of the room allows us from any position to see both a higher level perspective and dig into the details. At the same time, we also try to have something more like information on demand and provide guidance to where you are. And we have speech transcription. We have, when you look at a screen or you're about to perform an operation, before you do that operation, it tells you what's going to happen in AR. And generally, there is too many things that you would like to show on those TV screens, but you don't have enough space. So generally, when a person goes next to a screen, they can get some feedback on the choice of the algorithms or some additional statistical information. And in certain cases, we have 3D UIs. So for instance, it's very typical to change quickly the number of clusters and see how they split and they merge. So we have like a slider where you can easily modify this parameter. How did we evaluate this system? So we had what I could call more of a pilot study, because we only had 12 data scientists, which is not enough to have some statistically significant results, but it's good to have some first insights. And we had two parts. The first one is EDA and virtuality continuum. The idea here is that we would like to see how much immersion do we need. And in this case, we had 4 individual tasks, so each person would actually do a separate task on his own. And in this case, we had a data set about Fitbit data. And the second part was a direct comparison, which are very rare in this field because it's very hard to find an equivalent for an AR/VR tool for these things. A comparison with I would say, state-of-the-art clustering EDA tool. And the idea here is trying to see if collaboratively one performs better than the other one. So for the first part of the study, we split participants so that some of them would work in different modalities. The first one was the physical environment. So no AR, no VR, just the space as it is. The second one added the integration of HoloLens devices. And then we completely removed the physical space, and we said, okay, this space is very expensive to build. Why don't we just get rid of it? Like, would it be perfect? We don't need caves anymore. We just have a $300 headset and that's it. I mean, maybe the HoloLens is a bit more, but the VR ones are cheaper. And so in this case, we have a virtual replica of the environment with the same exact functionalities, even though, for instance, touch is replaced by air tap and similar equivalencies. And then we finally have the VR version. So let's go here. So what happened? Again, these results need to be taken as like suggestions more than a scientific proof. But for instance, what we noticed is that hybrid reality concretely decreased the task duration. So it actually has a positive effect, it seems. But at the same time, AR and VR standalone version underperformed compared to all the other possibilities. And this gives us an idea that despite the excitement about the VR, we are still not ready to have these technologies replace existing technologies. Some of the reasons are interaction. So air taps, gaze-based pointing, ray casting onto the interfaces from the long distance, terrible idea. Generally, people prefer to use touch, walk to a screen and actually touch the screen. or use the keyboard, because in certain cases it's actually easier to use. For filtering, it's easier to use a keyboard. Since we are trying to leverage tasks in which you need to look at multiple data views at the same time, having a small field of view is really a problem, because I want to see this in combination with this, and then I see only a slice of the data points, and then I need to rotate my head continuously, and this is not really practical. At the same time, we generally say, oh, the resolution of these devices has increased a lot. That's still not enough for certain things. So for instance, if I'm looking from the mid-distance, a statistical chart, some text, something that requires more resolution, that's not going to work. So that's why there are still higher resolution environments, caves and so on.
In this video, we quickly introduced the dataset participants in our user study.
Sorry, didn't know audio was present. So the second part of the study involves a comparison with cluster file. Here you can see a quick example of how it works, but the idea here is, instead of having many tasks, we have one collaborative task, which is actually long and complex enough. The task was to try to identify from a data set of UPDRS scores for people with Parkinson's disease, which could be the phenotypes associated to Parkinson, which is an open question. There is no solution to this question. And in this case, we try to evaluate both the time performance, but mostly the insights. So if we go to the results, you're going to see that we actually did have a good improvement in terms of time performance as a team. But I would say that the most interesting thing is that the insights collaboratively generated with this type of environment is actually a superset of the environments of the insights generated with cluster file 2. So in short, we could say that we had more insights and in less time. But this is due to a complex combination of different things, at least according to us. We had better contextualization. You could see more things at the same time. Normally, on cluster file, you could work only a few slices of the data at the same time, and then you could overflow the screen. The table helped a lot in terms of reproducibility, collaboration. There were less parameter changes, less trial and error attempts. But on the other end, we had some issues with the headsets. So their use was intermittent, and there was some discomfort. There were people saying things from, oh, it's going to ruin my hair, I don't want to wear it, to, I could personally live 24 hours a day with a HoloLens on my head. But there were people that was, after 2 minutes, this is too heavy, which is something that personally, it's hard for me to understand because I don't feel this problem. But apparently it happens. And then there were super funny things, such as a guy did a Bloom gesture and it quits the application of the HoloLens devices. Plus some difficulties with text input and other factors involving the HMD. So for instance, we noticed that people were supposed to take HoloLenses from the table and use them personally. Instead, one person would take a HoloLens and then say, oh, okay, and then give it to another person, which is something that we didn't expect. So I think it would be nice to follow up with a future user study in which we test more things and we go deeper into this. To close quickly, so we noticed that AR and VR have a potential to benefit various aspects of data analysis. At the same time, we noticed that standalone AR VR experiences are not suited, at least at the moment, for replacing existing technologies. We still have hardware design interaction challenges, and we need to admit that certain tasks are much better done with a keyboard and a mouse. So in this sense, I think that our community should continue try to research appropriate ways to apply AR and VR to data science. And when I say this, I mean creating new interaction paradigms. Avoiding things such as, oh, I used to do this on a 2D screen, I'll try to port the same thing to VR. Those things are not always going to work. So for instance, like we saw for the case of raycasting on 2D interfaces. And however, in the meantime, I think that we should think of AR and VR as a complement to what already exists and try to develop systems that allow you some flexibility. So for instance, I'm a data scientist, I would like to write my code in Python, and then maybe in certain cases I would like to have a 2D type of visualization, and then maybe at a certain point I would like to dig deeper and wear my headset. So I don't think we should constrain people to use only AR or only 2D or only coding, but they should be able to pick whichever modality of interaction and visualization they want, depending on the type of data and their task. And I thank you for your time, and this is it. As Gan said, I recently moved to Apple, so if you want to know how this project unfolds, you can contact Mark Podlasek, which is the manager of the data space. And thanks again.
Thank you, Marco. We do have time to take some questions. Any questions from the audience?
Hi, looks amazing. Congratulations. Quick question on the evaluation, because maybe I missed it. You were evaluating with groups, right?
In the second part of the study, yes.
Yeah.
I skipped it because it was it's much easier if you read the paper because it's a bit intricate how because it is generally hard to evaluate it. I'm gonna make it brief, but pretty much we divided people into groups based on what they call analyst archetype. So you generally have sort of different levels of, I wouldn't say experience, but different levels of how people approach problems.
Right.
And they are divided into 3 groups based on that way, and either way they are balanced. For the first part of the study, they were just, for the results, they were grouped into archetypes, but everything was done individually. So we had 4 people perform in a modality, 4 people perform in a modality, and so on.
So they would do it individually and then communicate about the results.
Yes.
So I see maybe you have some insights on this, that this type of environment where you have big screens and a table would be good if they're looking into the problem and talking to each other at the same time. You have any insights if that's the case?
Second part of the study.
Right.
So the first part, the idea was just make them do single tasks individually and see what performs best in terms of technology. The second part was pick the one that performed the best, which was the hybrid reality version. We would have liked to do it for everyone, but we didn't have enough participants. And in that second part, there were actually 4 people around the table, and they were interacting with each other, and they were balanced in terms of archetypes, and then they would communicate with each other. And then you can see more about the rationale of like this user study design. But they would decide when the session was over themselves and say, okay, we are done with this, and then we would make them list the insights.
Thank you. Make sure to read the paper.
Thanks.
Any other questions? I do have a question. So I think overall the conclusion is the hybrid does help improve performance, but AR VR alone is not yet enough for used independently. Would you see as the hardware advances in terms of resolution, field of view, and all those things, would it become more feasible to or suitable to use as independently, or do you still think there will be a value for having a physical display?
Okay, so I'm a bit torn on this answer because I personally I come from a lab where they developed the CAVE 1 and CAVE 2 systems, and I have some particular affection for immersive environments. At the same time, by working on this type of environments, I always have issues in justifying them. Having people coming and say, "Oh, why don't you just use a AR/VR headset?" I think there's been already big improvements. If you check one of my first slides, there is a pic taken from a startup called Virtualytics, which I think is doing a great job in this space, and even with the current technologies, they're actually doing some good product. I think that probably the next wave of devices is going to have better resolution. We are going to have to work more on text rendering, eventually try to find, as I said earlier, try to not just to copy paste what we did in 2D, but try to find new ways to interact with it. So I think it is probably possible.
So
I just want to follow up what you just mentioned, right? So you said that the big problem for the AR and VR users was the interaction actually with the interfaces, because people like the tactile thing of touching the screens and so on. And it's, of course, now it's the problem of the gorilla hands, or whatever we call them, air taps. But there is a new devices are coming on the market that will allow you to have a bit more tactile things. What would you reckon? How much this would affect your study, having a bit better interaction with the interfaces?
So that's perfect, and it allows me also to add a note. So for instance, if you check at the charts they made, again I said, take them as a suggestion. So for instance, it is very hard to evaluate these things, especially in this case. You will see this result and you will say, oh, AR was terrible. But something that, if you read the paper, you will notice is that in this case, for instance, we didn't even we didn't have the HoloLens clickers. So we could say, how would the results of this study be if we had the HoloLens clickers? That would have removed all the problems that we had with the air tap gesture. So going back to your question, probably it will have, I would say, a relevant impact. So that's why I say that it would be nice to redo in a little bit this user study, maybe with more people, introduce more modalities, and have more modalities for all of them.
Actually, I think your setup is fantastic to test these kind of scenarios, right? So just repeat as an experiment with this.
One last question.
Just a quick question. Curious, do you think that the types of charts and interactions that you have the users doing has a larger effect on how they interpreted the interfaces versus, I guess, the larger conclusion that the interface was better or less useful? I see a lot of different charts and different interaction types. I'm just wondering if having so many different ways of interacting has had some effect on the conclusion.
So it's a bit of a hard question to answer. I think definitely yes in a way, but it's hard to estimate how much. Meaning that pretty much the interface for Immersive Insights has been inspired by the cluster file tool, which we knew it worked well internally at IBM. And in that case, you would use much fewer views at the same time, and the way we would use it was different in a way, because you would never have so many things at the same time. You would never interact with so many things and contextualize at the same time. So I would say that this is sort of experimental, and there might be some bias in how the results show based on the user interface design. So I think that if I had to do this a second time, I would probably reiterate another time on the UI design.
Okay, thank you. Please